In the vast cosmic theater, our sun is the star of the show. It's the powerhouse of our solar system, the giver of light, warmth, and life. For millennia, we've looked up at this brilliant orb, wondering about its secrets. But how do you study a star up close? How do you get near a ball of fire that's, millions of degrees hot? You build a ship unlike any other. You build the Parker Solar Probe. This audacious mission is humanity's first real attempt to touch the sun, to fly right through its outer atmosphere and send back answers to questions we've been asking for generations. It's a journey into the heart of our stellar neighborhood, a quest to understand the very engine of our world. Long before we could build a spacecraft to brave the sun's fury, one man imagined what was happening there. His name was Eugene Parker. Back in the 1950s, scientists believed the space between planets was just an empty void. But Parker did the math. He proposed a radical idea, that the sun was constantly spewing a stream of charged particles in all directions. He called it the solar wind. At first, many didn't believe him, but space probes later proved he was right. The solar wind is real, and it travels through the entire solar system. NASA named its solar probe after him, a fitting tribute to the visionary who first imagined this invisible river flowing from our star. The Parker Solar Probe has a grand to-do list, a set of cosmic puzzles it was built to solve. First, it wants to understand one of the sun's greatest mysteries, the corona. The sun's surface is about 10,000 degrees Fahrenheit, but its atmosphere, the corona, is millions of degrees hotter. How does it get so hot? It's like a bonfire being cooler than the air a few feet away. The probe is designed to fly right through this superheated region, to find out how energy flows from the sun and heats up the corona to such extreme temperatures. It's a fundamental question about how stars work, and we're finally close to an answer. Another major goal is to solve the puzzle of the solar wind. We know Eugene Parker was right about it, but we don't know exactly how it gets its incredible speed. The solar wind starts out slow near the sun's surface, and then accelerates to over 1,000,000 miles per hour as it travels out into space. What acts as the cosmic gas pedal? The Parker Solar Probe is designed to fly through the very region where this acceleration happens, taking direct measurements. It also studies the sun's powerful magnetic field, a tangled web of energy that drives everything from solar flares to the solar wind itself. Understanding these forces is key to understanding our star. Getting to the sun isn't as simple as just pointing your rocket and hitting go. The sun's immense gravity pulls on everything in the solar system. To get closer to it, a spacecraft launched from Earth has to slow down its orbit around the sun. Imagine you're on a cosmic merry-go-round. To move closer to the center, you have to slow your spin. The Parker Solar Probe needed to shed an enormous amount of orbital speed. To do this, it embarked on a clever, winding path through the inner solar system, using a cosmic dance partner to help it along the way. It's a journey that requires patience, precision, and a little help from our planetary neighbors. The probe's secret weapon for this journey is the planet Venus. On its multi-year voyage, the Parker Solar Probe performs a series of flybys of Venus. Each time it swings past the planet, it uses Venus's gravity like a slingshot in reverse. This is called a gravity assist. Instead of speeding up, the probe is carefully angled to allow Venus's gravity to pull on it and slow it down, tightening its orbit around the sun. With each pass, the probe's path gets smaller and smaller, bringing it closer and closer to its fiery destination. It's a brilliant use of the laws of physics, a cosmic ballet choreographed by scientists and engineers back on Earth. This journey is fraught with peril. As the probe gets closer to the sun, the environment becomes incredibly hostile. The radiation is intense, capable of frying ordinary electronics in an instant. The heat is unimaginable, reaching temperatures that can melt steel, and the probe is traveling faster than any human-made object in history. At its closest approach, it will be screaming through space at over 430,000 miles per hour. That's fast enough to get from New York to Tokyo in less than a minute. The probe has to survive all of this, while keeping its sensitive instruments cool and functional. A monumental engineering challenge. Then, in 2021, the Parker Solar Probe did something no spacecraft had ever done before. It crossed a critical boundary known as the alpha and critical surface. This is the point where the solar wind becomes supersonic. That is, it moves faster than the waves that travel through it. Below this boundary, the probe was officially inside the sun's atmosphere. It was touching the sun. For the first time, we were no longer just observing the solar wind from afar. We were inside it, feeling its flow and measuring its properties directly at the source. It was a historic moment, like the first time an explorer dipped their hand into a previously unreachable ocean. Once inside the sun's corona, the Parker Solar Probe began to experience the sun in a whole new way. One of its most exciting discoveries came from observing the solar wind at its birthplace. Imagine a river with chaotic eddies and currents near its source that smooth out as it flows downstream. The probe found something similar. Close to the sun, the solar wind is a messy, turbulent place, with particles whipping back and forth in switchback patterns. These S-shaped kinks in the sun's magnetic field lines are like energetic whips, flinging particles out into space. The probe flew right through these structures, giving us our first direct evidence of how the solar wind gets its initial push. The probe's journey also revealed secrets about the sun's magnetic field. We often see diagrams of the sun's magnetic field as smooth, graceful lines looping out into space. But the Parker Solar Probe found that up close, it's a much more complicated and tangled mess. The switchbacks are a key part of this. These sudden reversals in the magnetic field seem to be a major source of energy, potentially contributing to both heating the corona and accelerating the solar wind. It's as if we've been looking at a smooth rope from a distance, and the probe has shown us it's actually made of countless frayed, twisted fibers, each buzzing with energy. And what about that baffling coronal heating problem? The Parker Solar Probe is providing crucial clues. By flying through the corona, it can measure the different types of waves and energy bursts that are present. Scientists believe that magnetic waves, vibrating and crashing into each other, could be releasing their energy as heat, warming the corona to millions of degrees. The probe's data shows evidence of these waves and other small-scale energetic events, sometimes called nanoflares. By sampling this environment directly, we're gathering the evidence needed to finally piece together how the sun's atmosphere gets so incredibly hot, a puzzle that has stumped astronomers for decades. These discoveries are not just abstract scientific facts. They are rewriting our textbooks. We are moving from theories and models to direct, concrete observations. Before the Parker Solar Probe, we were like people standing on a distant shore, trying to guess the ocean's temperature and currents by watching the waves. Now, we have a thermometer in the water. The probe's data is giving us a high-definition picture of the sun's immediate environment, revealing a dynamic and complex system that is far more active and intricate than we ever imagined from our vantage point, 93 million miles away. It's a new era of solar science. How does a spacecraft survive a trip into the sun's atmosphere? The answer lies in some truly brilliant engineering. The hero of the mission is its thermal protection system, a revolutionary heat shield. This shield is about 4.5 inches thick and made of a carbon composite material. It's designed to face the full fury of the sun, withstanding temperatures of nearly 2,500 degrees Fahrenheit. While the front of the shield gets incredibly hot, the spacecraft and its instruments hiding in its shadow remain at a comfortable room temperature. It's like standing behind a perfect parasol on the hottest day imaginable, allowing science to happen in one of the most hostile places in the solar system. Keeping the probe powered is another challenge. Most spacecraft use solar panels, but how do you keep them from melting when you get so close to the sun? The Parker Solar Probe has a unique solution. Its solar panels are mostly retracted behind the heat shield during the closest approaches. Only a small part of the arrays peeps out into the intense sunlight, just enough to generate the power needed. The panels are also actively cooled by a circulating fluid, a first-of-its-kind cooling system for a spacecraft. This combination of shielding and cooling allows the probe to draw power from the very star it is studying without being destroyed by it. The discoveries made by the Parker Solar Probe are not just about the Sun. They are about us. The solar wind and solar flares it studies can have a direct impact on Earth. These energetic events, known as space weather, can disrupt our satellites, knock out power grids, and endanger astronauts in space. By understanding how these events are born at the Sun, we can get better at predicting them. This mission is providing the foundational knowledge we need to protect our technology-dependent civilization. It's about understanding our home in the cosmos and the powerful star that governs it, making our own world safer in the process. In the end, the Parker Solar Probe is more than a machine of metal, wires, and silicon. It is an extension of our own curiosity. It represents the human drive to explore, to journey into the unknown, and to understand our place in the universe. By touching the Sun, we are connecting with the source of our own existence. Every piece of data it sends back is a page in the grand story of our star, a story that is also our story. The mission continues its daring journey, spiraling ever closer, promising even more profound revelations about the fiery heart of our solar system. The secrets of the Sun are finally being unveiled,